Hello and welcome to I Know Dino. I'm Garrett.
And I'm Sabrina.
And today, in our 397th episode, Sabrina is going to tell us all about how to find fossils.
Yes, as well as dinosaur of the day, Saurornitholestes.
Very nice. But before we get into all that, we want to thank some of our patrons for helping us to create this deep dive episode. And this week, we'd like to thank Ranger Chris from Dino for Hire, Viatis, James, Sarasaurus Rex, Jesse, Christine, Sophie, Laurasaurus, Vincentrosaurus, and JC.
Awesome. Thank you so much, everybody, for supporting our show and also just for sharing your love of dinosaurs with us. All right, I pulled a Garrett here and did a deep dive, went down an Dromaeosaurids burrow on how to find fossils. It started with how to find fossils, and then I decided to go expand a little bit more on what are fossils and what do they look like and things like that. I will say that the main sources, which we'll link to in our show notes at iknowdino.com if you want to see for yourself, is the book Fossils, A Guide to Prehistoric Life, which was a really great resource that points to other resources so you can also go down your own burrow. There's a lot of great photos and descriptions. It goes through different time periods, vertebrates and invertebrates, and plant fossils. And there are a few apps and websites that can help you with when you're going on fossil digs or if you want help with identifying fossils that you found. That includes the app Fossil Explorer, the website My Fossil, and the website The Fossil Forum. So I'll start with, what are fossils? Well, fossils are the remains or traces of the remains of animals and plants, basically all organisms, because that includes bacteria. I don't know where bacteria falls.
I think they're an animal, maybe. I don't know, they're a living thing.
That's true. The word fossil comes from the Latin word fossis, which means to dig, or fossilis, which means obtained by digging. Fossilization can happen a few ways. So one example, let's just say a dinosaur dies in a lake, because, we got to talk about dinosaurs. And then the organs and the fleshy parts decompose, and the skeleton stays intact at the bottom of the lake. Then sediment builds up, protecting those bones from scavengers, and minerals from groundwater slowly replace those bones. More sediment builds up over time, and eventually the bones and the sediment layers become bedrock. And eventually, those bones are found via erosion, or they're excavated. Fossils can be large or small. They can include bones, shells, feathers, leaves. There are microfossils. That includes things like bacteria and pollen. And then there are macrofossils, and that includes dinosaur bones and petrified trees. And on a side note, fossil wood may or may not be petrified. Fossils can vary in age. They're often talked about as young as being 10,000 years old or as old as 3 or 4 billion or more years old. And we get into more detail about how long it takes to fossilize actually in next week's episode. So stay tuned.
It's going to be my fun fact.
Now, not everything fossilizes. In fact, most things don't. There's some luck that's involved when it comes to becoming a fossil. You do need the right conditions.
There's a lot of luck, because most times when things die, they are not in the right conditions to become fossils. A lot of times people talk about how statistically fossils just don't happen.
Yes.
Like you wouldn't expect to ever find them if you're looking at typical processes in nature.
There were a few sources I found that said that less than 1/10 of 1% of all species that ever lived became fossils. So that gives you an idea of how rare it can be. Although other sources were saying, fossils actually aren't that rare if you look at how many we've found. So anyway.
Definitely depends on the type of animal. That's the other big factor in it. If you have no hard, bony parts in your body, you're really unlikely to be a fossil.
Yeah, but, there's other kinds of fossils other than the hard, bony parts.
True.
And most fossils that have been found are of marine animals, like shellfish and sharks. When it comes to dinosaur fossils, a lot of dinosaur fossils were from animals that lived near a lake or river. Maybe they died before a flood and were quickly covered in mud and silt, or they were washed into a river by heavy rain. Not many dinosaurs are known from, say, mountain or jungle habitats, which is too bad. I'm sure there's some weird ones.
Yeah, definitely. Yeah, so that's that. We might be getting a biased fossil record, or we definitely are getting a biased fossil record based on which animals lived in the types of areas which easily fossilize.
There are multiple types of fossils. There's the kind that we usually talk about on the show, the body fossils. That includes bones, teeth, and shells. There's also mold fossils, where you can see the bones or shape or parts of an animal's body or plant. Then there's soft tissue fossils. That includes preserved skin, muscle, bone, hair, internal organs. Basically, something's buried really quickly and not scavenged, and there's not much oxygen in the environment, so it doesn't decompose. And that often happens when something's buried in volcanic ash or ice or bogs, or they're stuck in amber. Some dinosaur eggshells, some soft ones, have been found where there's thin carbon layers in the rock, and those are the soft tissue. Then there's ichnofossils. That includes eggs, nests, tracks, burrows, coprolites, teeth marks, scratches, footprints, gastroliths, imprints of leaves or skin. So many things. And you can learn a lot about the behavior of something from ichnofossils.
Yeah, and all those things are fossils. Fossils aren't just the bones. They can be any of these types of things.
Exactly. However, fossils are usually rock made out of minerals, and they're not the original bone material.
They do often include some of the original material, though. It's not all the original material, but especially some of the compounds that include calcium, for example, can last a really long time. So like tooth enamel, for example, can be the original enamel from the tooth, but the rest of the tooth might be replaced by other minerals.
True. Oh, and then there's also index fossils, also known as guide fossils, and those are the fossils that are used to define and identify geologic periods. There's different sediments that look different depending on the conditions they were deposited in. So if you find an index or a guide fossil, that can tell you, oh, these are the other kinds of fossils I might find in this layer.
And then you know which formation you're in.
So to get all these types of fossils, there are different ways that fossilization happens. Most fossils that we talk about happen through permineralization. And the gist is that an animal or an organism dies, it's quickly covered by sediment. It could be mud, sand, volcanic ash, tar, so that it's not scavenged and it's not in a dry area or it doesn't get weathered away at the surface. And then over time, those minerals carried by groundwater fill up the space inside the animal and crystallize, replacing the bone or most of the bone.
And again, it's not necessarily the bone itself. It can also just be the spaces in between bones. So bone, in a way, is largely a living tissue with all the blood vessels and everything in it, but that stuff has to or will decay pretty rapidly. So it needs to be filled and replaced by other things so that the bone doesn't just crumble apart. And it depends on what kind of minerals are there, how that happens.
Yes. Then there's impression or cast and mold fossilization, where the bone or tissue gets removed after an animal or a plant is buried, such as through groundwater flow.
So that would be the difference there is in permineralization, the groundwater and the minerals have to be basic, basically, because if it's acidic, it'll just dissolve the calcium. And so you're talking about the dissolving component now, but yeah, that's sort of the distinction there is the acidity of the water can make a big difference.
Yeah, so then in this case, with the cast and molds, the organism decomposes completely and the bone dissolves. And if there's an empty space that's in the shape of what was that organism, that is a mold fossil. But if minerals or a new sediment fills in the space, it's a cast fossil.
Oh, yeah. So if the rock around the original thing actually fossilizes or turns into rock, then yeah, it's considered a fossil. That's really interesting, even though it actually is just the thing that was around.
But you still have that impression. You know what it looks like.
Yeah.
Then there's endocasts or internal molds. That's when sediments fill in the interior of an organism and preserves a 3D mold of the inside. And we use that term when we're talking about dinosaur brains sometimes.
Yeah, the endocasts of the skull, cranial endocast. So it's like the brain decayed away and then a bunch of mud flowed into its head.
Yep.
And cast it in place. And then you had that acidic water or something come through, eat away all the bone, but you've got that remaining endocast or the brain cavity.
Yeah, and you get a lot of details. There's unaltered fossils, which are rare, but that happens when something's trapped in amber or tar, it's dried out, or it's frozen. Think preserved woolly mammoths, kind of frozen. Teeth are a good example of an unaltered fossil because it's the hardest part in a vertebrate body. Sometimes amber can trap an organism in tree resin, and then it hardens and preserves the fossils. And sometimes you can find mummified fossils with the soft tissue.
Although, yeah, even though they're considered unaltered, they are in a way because you can see them in a very lifelike way. But the chemistry still tends to break down over time, which is why you can't Jurassic Park the blood out of an amber mosquito because the DNA will just decompose just because of entropy.
But compared to a cast or a mold, it's unaltered.
Yes, yes.
Fossil sites with really good soft tissue preservation, those kinds of fossils, are often called Lagerstätte, which means storage place in German.
Archaeopteryx is a really famous Lagerstätte.
Yes.
Or comes from, I should say. It's not the only one.
Right, the Solnhofen limestone, Jurassic Age. And these sites, they may be from organisms being buried in, again, that low oxygen environment with very little bacteria, so it's very slow to decompose.
Yeah, and a lot of times it's a really fine sediment too, which helps preserve some of the detail of the fossil.
Yeah, like sandstone or something. There's other types of fossils and fossilization. There's subfossils, which has organic material. It's not done fossilizing, and that can be used for radiocarbon dating or extracting and sequencing DNA or protein.
Interesting. I've never heard that before. So that's something that's not fully mineralized yet?
I think that might be for some younger fossils.
Yeah, not dinosaurs.
Yeah.
Or not non-aviate dinosaurs.
Then there's chemical fossils or Chemo Fossils, where chemicals found in rocks and fossil fuels like petroleum, coal, natural gas, and they provide an organic signature for ancient life. There's derived or reworked fossils. That's a fossil found in rock that accumulated much later when the animal or the plant died. So the fossil eroded and then got redeposited in a younger sedimentary deposit. There's molecular fossils that preserves organic material and it has chemical data, but there's no information on the structure of the organism. There's autogenic, that happens quickly without moving the organism, so it happens in situ, and it's special mineralization that makes really precise molds and casts. There's replacement, where shell, bone, or tissue is replaced with another mineral, usually gradually, so the microstructure is still preserved. So for example, the calcite of an oyster shell gets replaced by silica, or the wood from the Petrified Forest National Park in Arizona, you can see the colors are produced from minerals that have been replaced. And some common replacement minerals are quartz, pyrite, dolomite, hematite.
Yeah, pyrite especially can be problematic because they call it Pyrite Disease because it's really hydrophilic. It'll absorb water and then it swells up. And if you've got pyrite in the middle of a fossil, it'll swell up and it'll break it apart like a rusting piece of metal through concrete.
Fool's gold strikes again.
I guess.
There's recrystallization, so there's a change in the crystal structure, but not in the mineral chemistry. For example, aragonite, a common mineral in shells, sometimes changes to calcite. This doesn't usually change the specimen too much, but fine details may be lost, and this happens a lot with marine invertebrate fossils. Those fossils are altered by pressure or heat. There's adpression, also known as compression impression. These fossils, they're the original material, but they've been altered chemically, and what remains is often a carbonaceous film. Now, sometimes that film is lost, and then all that's left is an impression, but a lot of times, both compressions and impressions happen together. So the fossils, they're basically flattened, they become 2D, but they still show the shape of the organism. And one example where you see this is with fossil ferns.
Yeah, sort of like pressing a leaf in a book or a flower in a book.
Exactly. Next is carbonization and colification, where organic remains have been reduced mostly to carbon instead of the original organic matter, and then a thin film forms a silhouette of the original animal or plant. And there's bioemulation. The skeletal organism overgrows or absorbs another organism, preserving it or an impression of it within the skeleton.
What?
I think we've talked about it before, but it's not been too common with dinosaurs, at least that I can think of. There's examples of it happening with a gastropod egg.
Another animal grew around the egg? Or the egg grew around something?
I think an example might be there's an empty shell, something else uses that shell, and then they fossilize together.
Oh, interesting. Okay. So it's something soft that wouldn't otherwise preserve, but then it gets included in the hard tissue of something else.
Yes, but we don't talk about it much with dinosaurs, so I'm not very familiar with this particular kind of fossil.
Not super relevant because dinosaurs have their own hard parts that can fossilize. They don't need to rely on another animal to help them. And they're big in general. That's really interesting, though. I've never heard of that before.
Yeah, those Dromaeosaurids burrows.
Yeah, I know how those go. Now we're going to take a quick sponsor break, but when we come back, you're going to tell me about what fossils look like and maybe what they don't look like.
Now that you know the types of fossils, and there are so many more types than I realized, well, what do they look like? First, I want to say that if you're looking for fossils, watch out for pseudofossils. That's where rocks look like bones or other types of fossils. They can sometimes look like an egg, like concretions or spherical nodules, or they have a horn or a bone-like shape, but they're not actually fossils. Fossil bones, however, have a fibrous or spongy texture on the inside, and that's why some people do the lick test, where you put the fossil or part of the fossil on your tongue, and if your tongue sticks to it, because the fossil has a porous nature, that means it's a fossil.
You can also lick your finger and touch it if you don't want to put random things in your mouth.
Yes, good point.
Because it's the capillaries from the original tissue, which are preserved because the actual structure gets preserved in a lot of cases, unless it's a mold or something like that. Then you can actually feel those capillaries pulling on you. It's really weird.
Yeah, it is weird. And mineral crystals in the bones, that's why fossils often have this porous or honeycomb-like texture. Fossil bones also have specific shapes you can look for. One example is a tibia bone, the lower leg bone, that has specific bulges at the end of them for cartilage and muscle attachment.
Yeah, it definitely helps to understand anatomy a little bit, because then you won't get tricked as easily by things that looks vaguely like a bone.
Mm-hmm.
If you can identify bones and say, like, wait a second, that doesn't make sense as a bone.
Yes. Not like me in elementary school brushing away dirt outside the playground and hoping to find something.
Well, I mean, I think that is a fair place to look.
Well, it turned out it was just hard pieces of dirt.
Oh, I see.
We got excited, but it was dirt. Now, sometimes fossils are small or fragmented, and it's hard to know if it's a fossil. And that's when knowing about your location is really helpful. Depending on where you are, you can know if you should be finding vertebrate or invertebrate fossils, or marine animals versus terrestrial animal bones, mammals versus reptiles, etc., or maybe even like specific types of mammals or reptiles. Also, when you're looking for fossils, look for something that doesn't look like everything else. Fossils, sometimes they're tan or pinkish sometimes because of the sun.
Yeah, and it really depends where you are, which color the different fossils will be. In some areas, all the fossils are like really dark, like almost black.
Mm-hmm.
Other places, like you said, they're pinkish or tannish or something. But if you have already found a fossil there, or you know about the locality, you can find a book or something, then you'll know what color to look for. It can be a really good clue.
Mm-hmm. And play a one of these things is not like the other game. When it comes to fossils and humans and relatives of humans, we've been finding fossils for a long time. Some examples, Neanderthals made necklaces of round fossil shells. Ancient Egyptians gathered fossils of species that resembled animals they worshipped, like the fossil sea urchin shells associated with the deity Sopdu the morning star, which is Venus in Roman mythology. The Plains tribes in North America had a lot of pterosaur fossils in the area, so that might have contributed to the mythology of the thunderbird. In medieval China, ancient mammal fossils were thought to be dragon bones and used as medicine and aphrodisiacs. In Norse mythology, echinoderm shells were associated with the god Thor. Georges Cuvier believed that most, or all, animal fossils that he studied were from extinct species, and he became a proponent of catastrophism. And in his 1796 paper on living and fossil elephants, he wrote, quote, "All of these facts, consistent among themselves and not opposed by any report, seem to me to prove the existence of a world previous to ours, destroyed by some sort of catastrophe," end quote.
There's a lot of interesting ideas people come up with when they find bones in the ground and they don't know where they came from.
Mm-hmm. Yeah, I do love hearing the different mythology stories around them.
Yes. The ichnofossil ones are my favorites. Like, what made these tracks?
Mm-hmm. So let's get into fossil hunting. We're looking for fossils now. You can be an amateur or a professional. You can do it as a hobby or for science. You don't need to be formally trained. Fossils are actually often found by accident, happy accidents. Sometimes fossil hunting is done for profit, and that is a controversial topic in paleontology. Sometimes it has been done illegally, and then fossils are repatriated. We've talked about fossils that get repatriated back to Mongolia as an example.
But illegal fossil hunting doesn't necessarily require exporting them either. Sometimes people illegally fossil hunt in an area where they're not supposed to, and they just keep them or they sell them to someone nearby.
Yes. So if you decide to go fossil hunting, when you do, make sure you follow local laws, get permits if necessary. Also check for precautions in the area. You want to do some research ahead of time. Like Garrett said, it's helpful to know some anatomy. It's helpful to know about the location. You can read scientific papers and books. So you have an idea of the types of fossils that you could find. You want to know your geography, the place, and your geology, the time period. Again, that'll help you figure out which animals lived in the area where you're searching, when they lived, how their environment looked, and you'll have a better idea of what to be on the lookout for.
Don't be surprised if you don't find dinosaurs right away, because in almost every rock layer, there's something else that's more common than dinosaurs.
Yes. But sometimes you get lucky.
Yeah, there are some that are pretty dense in dinosaurs, but yeah.
If you're in the US, a good resource is the US Geological Survey. They've mapped out rock layers in the country, and there's an interactive map. If you are looking for dinosaur fossils, you want to look for sedimentary rocks from the Mesozoic.
Definitely. You're not going to find non-avian dinosaurs anywhere else, really.
Yes.
With some exceptions.
Oh, yeah, if it got refossilized or reburied.
I've got a fun fact about another type of rock other than sedimentary rocks. But definitely Mesozoic. That is the only time you'll find a non-avian dinosaur fossil. So if you're in, say, Scandinavia, or most of Scandinavia, where all of the rocks going back about 1 billion years have been scraped away, you will never find a dinosaur in those rock layers.
Oh.
And if you're in other parts of the world where there's still kilometers or miles of rock on top of the Cretaceous rock, you're not going to be able to find a dinosaur either. But you could find something else cool, like a mammoth or something.
Yeah. Or some kind of marine animal.
Mm-hmm. Yeah, there's lots of cool marine stuff.
When you do go fossil hunting, make sure you have the right tools with you. I've got some examples here, but I don't think it's a exhaustive list. So if you want to remove some rock, you want a geohammer that can help break up the rock that the fossils are in. You can also use a hammer and chisel if there's a specific part of the rock you want to break. If you're working really close to the fossil, you can use a pick to move tiny bits of rock, or an anvil, or tweezers for moving really small bits of bone that have broken loose. You want to make sure you don't lose any of those bones. Screens are helpful if you're sorting through small loose fossils.
We were actually using toothbrushes when we were on our site looking for little eggshell fragments too.
Yes.
And other brushes.
Yeah, that's also good for cleaning the fossils or making sure your site's clear and your work area is clean. Safety goggles. Some people have recommended glue or super glue. Occasionally something breaks. You want to fix it on site while you know where the pieces are supposed to go.
And if you want to be really proper about it, you might want to get a polymer glue instead of like off-the-shelf super glue, because sometimes people will glue fossils together and then it becomes a problem later because they are either glued incorrectly or the glue is so strong that it damages the fossil in one way or another. So yeah, there are some standards out there for the best glues to use.
True. You might want to have something to protect your fossil for wrapping it up. That could be like toilet paper, newspaper wrap, some kind of protective coating. Containers for transporting the fossil. For bigger-ish fossils, maybe a takeaway container. Some people have also said a film canister for smaller fossils. Having a backpack to carry them all can be helpful. And sticky notes, so you label the fossil. You want to label what the fossil is. You can also write on the fossil with a Sharpie on the rock or use whiteout and a pen. And a field book. You want to write down just everything you do. Have a record of what the fossil is, where it was found, what it looked like when you found it, when it was found, what conditions are when you found it, any other relevant information.
And taking pictures is good too, since everybody pretty much has a camera in their pocket at all times now.
Yes.
That's easy.
And also bring food and water is helpful. Compass, first aid kit, pocket knife, and maps. Road maps, topographic maps, geological maps.
Yep, that sounds like the 10 essentials, or at least a few of them.
Mm-hmm.
Also, you want like, the extra clothes and probably a flashlight. All the things that are good to have when you go out on your own or in a group even.
So there's a lot of things to consider. When you're out there looking, it helps if you're getting low. You want to be observant and then again, document everything when you do find something. Position, shape, size of the fossil. It is helpful that you don't have a particular goal or a particular fossil you're looking for because you never know what you might find.
Yeah. You can't really go out saying, I hope I find a hadrosaur skull.
Yes. And you could, but just be open about what else you might find.
Yeah.
Again, when you're removing fossils, you want to do some prep work first. For example, you might need some of those special adhesives to fill in some cracks, keep the fossil stable when you're removing it from rock. If you've got a larger fossil, you might need to create a field jacket to protect it so it can be moved from the field to a museum or an institution where the fossil will be prepared.
Oh, that's getting fancy.
Yes. I think that might be more rare unless you're working with a museum already.
Yeah, those are some advanced techniques. BYO plaster jacket.
Yes. In that case, you probably want to document where you found the fossil and then contact somebody.
I think so, yeah.
When it comes to where to find fossils, finding fossils takes a lot of hard work and patience. You have to know where to look, and then, of course, you have to have some luck. You also want to make sure you wear the right clothes for the environment.
Yeah, for me, that's wearing a big hat, a nice wide brim hat so that the sun doesn't burn me to a crisp. And that is a very common thing you see with paleontologists.
Mm-hmm.
Not even necessarily when they're just in the field. Some of them just wear them to SVP and other indoor places because they're so used to their big hats.
Yeah. And then again, make sure you follow local laws. Try not to go fossil hunting alone. And also stay away from animals that you think could be poisonous. Different hazards and depending on where you are. If it's your first time going fossil hunting, you might want to go on a guided fossil hunt, like with a museum, though I think you usually need to pay to do that.
You can also join like clubs that are going looking, or you could even just go out with a friend. If you're really into it and your friend is just looking for a nice hike, you might be able to combine forces that way.
True. If you end up going to a quarry or private property, make sure you have permission first to go there. And be careful of any falling rocks or any kind of traffic in the area. And then again, like we said, with the bigger fossils, if there's any kind of rare fossils or vertebrate bones you find, just leave them intact and contact somebody at a museum or some kind of professional to help. You do want to go to places where sedimentary rocks of the right age are exposed, like river valleys, cliffs, hillsides, quarries, road cuttings. Fresh exposures of rock are good for collecting, like in road or railroad cuts. People have visited mine dumps or quarries, places where rock is being excavated for new construction, riverbanks, and other natural exposures. But again, be careful. If you're looking for dinosaurs, dinosaurs are mostly found in rocks that formed in swamps and river valleys. And just keep in mind that every site is different and requires different techniques. And just as an aside, the reason we can find fossils is because of uplift. The tectonic plates collide, the form mountain ranges, or rocks get pushed up by new rocks forming under them, or there's also weathering and erosion from wind, rain, ice, heat, rivers, and then you see something sticking out, and that's how you know. I've got a list here of some places where you can find fossils, but it is by no means a complete list. It's also very US heavy. You can find fossils pretty much anywhere, even in your own backyard, or at least near it. And we talk about that in our interview in next week's episode with Cameron, so giving you a few hints of what to expect in next week's episode. First place I'll list is the Jurassic Coast and the Isle of Wight in the UK. It's good to go in the winter. Storms cause more erosion, but you want to check the tides. The safest time to go is when there's a falling tide.
Basically on the way to low tide.
In the US, there's a bunch of places, like the Big Brook fossil site in New Jersey. That's from the late Cretaceous. You can find shark teeth, mosasaur teeth, and teeth of extinct fish. There's the Westmoreland State Park in Virginia for Miocene fossils, shark teeth, crocodile teeth, whale bones. The Cedar Creek State Park in Waynesville, Ohio. And you can find trilobites, brachiopods, gastropods. You do need to get a permit from the Park Visitor Center. There's Post Oak Creek in Sherman, Texas. You can find shells and shark teeth. Montour Fossil Pit in Pennsylvania for Devonian fossils, trilobites, snails, brachiopods. The Florissant Fossil Quarry in Colorado. You can find plant, insect, some bird fossils. You do have to pay to dig. Capitola in California for Pliocene fossils. You can find snails, clams, sand dollars. Wardensville in West Virginia for Devonian fossils. They've got trilobites. Peace River in Florida has shark teeth. Mason Creek area in Illinois for plant fossils. Perth State Park in Maryland for Paleocene fossils. There's shark teeth and snail shells. And Warfield Fossil Quarries in Wyoming for Eocene fossils, like fish. There's also an interactive website we found where you can go and figure out where to find fossils in your state.
Oh, cool. Yeah, and I noticed that list doesn't really have any dinosaur spots on it, but that's because usually when you're looking for fossils, you don't find dinosaurs. It's pretty uncommon. You're way more likely usually to find stuff like shark teeth. That came up in so many of yours. And that's partly because the fossil record is really skewed towards more recent stuff. The farther back you go in time, the less likely you are to find stuff. And it's also skewed towards hard things that there are a lot of, like shark teeth or, invertebrates, and also marine stuff. So all those things are sort of working against finding dinosaur fossils. Plus, a lot of the places that have a lot of dinosaur fossils are either now state parks where you're not allowed to go look for fossils, or they're on private land, so you have to get permission to do it. But that doesn't mean you can't do dinosaur digs. It just means that usually you have to go, like Sabrina was saying, with a group.
Some institution, somebody who's affiliated.
Yes. But that can be good too, because then they'll help you find the stuff and you're way more likely to be working on a dig site that's already exposed.
Mm-hmm.
So you're likely to actually be able to work with some actual dinosaur fossils rather than just sort of wandering around hoping you might strike it rich.
Yeah, and that's how we ended up looking for eggshell fossils in Montana.
Mm-hmm.
Just through a museum. Plus, they'll give you some lessons on what to look for. And it's cool to see the science in action.
Yeah, definitely. Yeah, it's just fun hanging out with paleontologists too.
Mm-hmm. If you want to start a fossil collection, you can find your own fossils or you can buy them in certain places. Again, follow local laws when you're searching for fossils. Sometimes you can take your finds home, but it's not always the case. Some easy to find fossils include ammonoids, they look like coiled snakes, brachiopods, those are marine animals with shells, corals, and trilobites. If you want to, you can put them on display, and then if you've got too many to put on display, consider storing them, like the smaller, maybe lower quality pieces, and it's helpful to keep them, if you're storing them, in boxes with padding or in drawers.
Or you can do like we do and just buy replicas of really nice fossils, like huge stegosaur plates that you can get for the price of basically like a tooth. And then the original will stay at the museum while you get to appreciate the amazing qualities of the fossil.
Mm-hmm. You can still see all the details.
Yeah. I think collecting teeth is a pretty good way to go, though, because dinosaurs and sharks and everything went through so many teeth that it's not a huge loss to science if some of the teeth are in collections, private collections, and they're really cool.
I think there's other types of fossils, too, that people typically collect, and it's totally fine.
Yeah, like those invertebrates you were mentioning. They're just so common that it's like everywhere.
If you want to connect with some people, there are some fossil clubs and forums. So I mentioned at the beginning of this, Fossil Explorer. That's a field guide to common fossils in Britain. They've got an interactive map, and it shows a list of fossils known from that area. That covers England, Scotland, and Wales. There's My Fossil. That's a community of amateur and professional paleontologists. You can collaborate and share information and get help with IDing the fossils that you found. And the Fossil Forum, where you can also post images of your fossil and get help with identification. So, to recap, fossilization can happen in a lot of ways, but one of the most common, especially for dinosaurs, is permineralization. And you can find fossils pretty much everywhere. Just make sure you're prepared and check your local laws. So if any of you end up going fossil hunting and find something cool, please let us know.
And we're going to get into our dinosaur of the day, Saurornitholestes, in a moment. But first, we're going to take a quick sponsor break.
And now onto our dinosaur of the day, Saurornitholestes, which was a request from PaleoMike716 via our Patreon and Discord, so thanks. It was a dromaeosaurid that lived in the late Cretaceous in what is now Alberta, Canada, and the US, Montana, New Mexico, Alabama, North Carolina, South Carolina.
Oh, eastern US and western US.
It looked similar to Velociraptor. It walked on two legs, it had sickle claws, a long tail, and a lot of feathers. But it had a shorter, taller, wider skull than Velociraptor, and it had pneumatic nasals.
So when you say shorter, taller, you mean shorter front to back, but taller top to bottom?
Yes, that's a good point. Yeah, Velociraptor had this longer, lower, more narrow skull. Velociraptor's legs, too, were about 15% shorter than Saurornitholestes. So Saurornitholestes is considered to be a mid-sized dromaeosaur. Is estimated to be 5.9 feet or 1.8 meters long and weigh about 22 pounds or 10 kilograms. It had longer legs and was more lightly built than other dromaeosaurs. It also had a relatively large brain and a large olfactory bulb, so it probably had a good sense of smell.
That taller head was making room for the brain.
And it was agile and fast. It probably had feathers. It had curved blade-like teeth and large teeth in the front of its jaws. Some of its teeth may have been for preening its feathers.
Yeah, those small ones in the front. A lot of times people talk about that. It's an interesting hypothesis.
There's two species. The type species is Saurornitholestes langstoni, and that was named in 1978 by Hans Dieter Sues. Saurornitholestes sullivani was named in 2015 by Stephen Jasinski. The genus name, Saurornitholestes, means lizard bird thief. The species name Langstoni is in honor of Juan Langston Jr., and the species name Sullivani is in honor of Robert Sullivan, who found a partial skull in 1999 in New Mexico of the second species. The nearly complete skeleton of that species was found in 2014 by Clive Coy. The first fossils of Saurornitholestes were found in 1974 by Irene Vanderloo in Dinosaur Park Formation. The holotype includes teeth, parts of the skull, 2 vertebrae, ribs, parts of the tail, and a part of the hand. This holotype was less than 30 bones. Saurornitholestes may have been the most common small theropod in Dinosaur Provincial Park, based on a lot of teeth and bones being found.
That's cool.
Yeah, more Saurornitholestes teeth and bones have been found than Dromaeosaurus.
And yet, most people know Dromaeosaurus, but not Saurornitholestes.
Yes.
Dromaeosaurus is also a lot easier to say.
Ish, yeah. I guess if you're used to saying these sorts of names.
Saurornitho is like kind of a marble mouth thing to get through.
So over the 25 years after it was named, 4 additional partial skeletons of Saurornitholestes were found for a total of 5 skeletons, but not much was known about the skull until the specimen was found in 2014. And that specimen was found less than 1 kilometer away from where the holotype was found.
Well, that's nice because that helps you to guess that it might be the same species or at least the same genus.
Yeah. So that specimen's nearly complete, except for the tail. It shows that the skull of Saurornitholestes was shorter and deeper compared to Velociraptor. Fossils have also been found in the Oldman Formation and Two Medicine Formation. A tooth was found in Moorville Chalk in Alabama, and teeth and part of a foot was found in North and South Carolina in the Tar Heel, Coachman, and Donahoe Creek formations. So that's how we ended up spreading it around all these states.
A tooth isn't particularly diagnostic, but I guess a foot is decent, depending on what part of the foot.
Yeah. In 2020, John Wilson and Denver Fowler referred skull material found in the Judith River Formation in Montana to Saurornitholestes, and that helped show that Saurornitholestes was, quote, biogeographically widespread and occupied both inland and coastal environments across the northern portions of the late Cretaceous western interior of North America, end quote. So going back to that second species, Saurornitholestes sullivani was found in New Mexico in the Kirtland Formation in 2014. That's different from Saurornitholestes langstoni because it had an even larger olfactory bulb.
Oh, wow.
In 2019, Phil Curry and Dave Evans studied the skulls of Saurornitholestes langstoni. And again, they could do that because of that 2014 specimen, which is, quote, virtually identical to the holotype where they can be compared. So that's good. The 2014 Saurornitholestes langstoni specimen was at least 8 years old and almost mature based on histology. They also found that the holotype of Zapsalis, a dinosaur named in 1876 by Cope, based on a tooth found in Montana, was actually Saurornitholestes. More Zapsalis teeth have since been found in other formations. The genus name Zapsalis means thorough pair of scissors, and the species name is abradans. That name means abrading.
Thorough pair of scissors.
Well, when it's based on a tooth, I guess that makes sense.
Very good at cutting, I guess.
But now it's considered to be Saurornitholestes. Curry and Evans said that there may have been, quote, at least 2 major faunal interchanges between Asia and North America during the Cretaceous, end quote. North American dromaeosaurids probably came from a different lineage than Asian dromaeosaurids, which also means that Saurornitholestes and Velociraptor were definitely distinct from each other. But in the past, Saurornitholestes was considered to be Velociraptor langstoni by some scientists. That's because the skull wasn't known for a long time. So Paul in 1988 synonymized Saurornitholestes with Velociraptor, although many people didn't agree with that.
And that's why the Velociraptor name made its way into Jurassic Park when it clearly wasn't a Velociraptor.
I don't think it was a Saurornitholestes either.
Yeah, it just sort of got expanded to other, and it was like, oh, Velociraptor is actually a bunch of dromaeosaurs. Maybe this will get included later too.
In 2006, Robert Sullivan named Saurornitholestes robustus, and that species name refers to the thickness of the bone. It was based on fossils found in New Mexico. But in 2014, Dave Evans and others found Saurornitholestes robustus to be an indeterminate troodontid. The holotype didn't have any diagnostic dromaeosaurid characteristics, and it had some features found in troodontids, and the size of the specimen was more similar to better-known troodontid fossils found in Alberta. Saurornitholestes had a puncture and pull feeding method. Angelica Tereses and others looked at the teeth of several Saurorosaurs to study their feeding behavior, Gorgosaurus, Dromaeosaurus, Saurornitholestes, and Troodon, and they found that microwear patterns were the same on the small and large theropods, so the biting movements would have been similar in all of them, where they puncture and pull. They sink their teeth in and move back or pulled their heads back to pull out flesh. They found that they put in quotes, Troodon teeth, were built in a way they couldn't handle struggling prey, or else they'd break, so Troodon probably went for small prey. Saurornitholestes, though, had distinct serrations on the teeth. The serrations on the back edge of the teeth were larger than those on the front edge of the teeth, and that could be why we can tell just by teeth if it belongs to Saurornitholestes. It also had a flat tooth with long ridges at the front of the mouth for preening. A Saurornitholestes tooth was found in a wing bone once of a pterosaur, probably a juvenile Quetzalcoatlus, which Quetzalcoatlus would have been much larger than Saurornitholestes,
Yeah.
so it's possible that Saurornitholestes was scavenging.
It does seem unlikely that a Saurornitholestes, which is, what did you say, 20 pounds, is taking down a couple 100 pounds of Quetzalcoatlus pterosaur.
Yes, even though it was probably a juvenile still.
Yeah, it just seems unlikely. I mean, maybe if it was just a hatchling, could be, but then
I don't think it was a hatchling.
Yeah, exactly. Probably would have swallowed that bone and you wouldn't even seen the teeth at the end.
But hey, if it's scavenged, never pass up the easy meal.
That's for sure.
In 2001, Jacobson described a Saurornitholestes dentary and found 3 tooth marks on the surface. 2 of them were made by serrations from another dinosaur's teeth. The serrations were too different to be from Saurornitholestes, so it's most likely that they came from a juvenile tyrannosaurid like Gorgosaurus or Daspletosaurus, which were also in Dinosaur Park formation. So you had one dinosaur scraping the teeth of another dinosaur.
Ugh.
In 2001, Rothschild and others did a study that found that only 2 of 82 Saurornitholestes foot bones had stress fractures, and 2 of 9 hand bones had them. So that's pretty good, at least for the foot bones.
It's good to have stress fractures?
No, that only 2 out of 82 of them had it.
Oh, I see. Yes, that is good. I guess. I don't know. It seems like that's still a lot of fractures.
Could be worse. Other animals that lived around the same time and place as Saurornitholestes include ankylosaurs, ceratopsians, ornithopods, theropods, oviraptors, as well as turtles and fish.
And our fun fact of the day is that you can sometimes find fossils in igneous rocks and metamorphic rocks, not just sedimentary rocks.
That is what you alluded to.
Yeah. So, like you said, sedimentary rocks are definitely still the most likely. So this isn't meant to say that if you're looking for fossils, you should be looking in igneous and metamorphic rocks, because they are real garbage compared to sedimentary rocks for fossilization. Because sedimentary rocks are formed in a way where they often quickly bury the thing that gets fossilized. And they also allow for water to reach the fossils, carrying minerals, and they're in the types of environments where things are more likely to fossilize. But I want to focus on igneous rocks because metamorphic rocks are a completely different story, and this fun fact would be way too long. So for igneous rocks are formed by magma, or if it's flowing on the surface of the Earth, exposed lava. Lava usually flows at around 800 degrees Celsius to 1200 degrees Celsius, or 1500 degrees Fahrenheit to 2200 degrees Fahrenheit. At that point, really, the difference between Celsius and Fahrenheit is like, it's horrible.
Right.
It doesn't matter which, really, all that much.
Too much.
It's way too hot for any soft tissue to survive, period. Any hair or feathers are just going to immediately burn off. Basically, since water boils at 1/8 of that temperature, even at the low end of the lava temperature, it's going to boil off all the cells and, basically all the soft tissue. And the only thing left of an animal would be the bones. Interestingly, I found quite a few places that were saying bones don't survive lava because it's so hot that it melts bones or melts animals to nothing.
Ooh.
That isn't actually true. So the best estimate I can find for the melting point of bone is about 1,670 degrees Celsius, or a little over 3,000 degrees Fahrenheit.
Wow.
Bone is an incredible substance that we create in our bodies. It's really amazing. And it's actually pretty similar to some of the hard shell structures that you see on other animals. It's a calcium dominant and also phosphorus mineral. So we're actually like growing rocks inside our bodies. It's really cool. Just like how coral grows rock, it's
Yeah.
like living rock.
Ooh, that's weird
We have
to think
that in our
about.
body too. Yeah, super cool. So it lasts for a really long time. That's why it's such an important thing. And, whenever we're trying to identify old bodies and stuff, you always go to the bones because that's around and they last for a really long time in a lot of situations. But they definitely don't melt. However, melting isn't the only thing that destroys structures. So, for example, if you have something made out of metal, and even if you don't get it to the melting point, it gets really weak. So there's a glass transition temperature that really softens things, and then they can get smashed really easily. I don't know what the glass transition temperature of bone is. I couldn't find that anywhere since bone is made up of several different minerals. I could find it for individual minerals, but not for bone as a whole. And you kind of need to know for the whole structure. So it's possible that at 1200 degrees Celsius, at that higher end of lava, that the bone would get soft enough that it could get squished. But I'm not sure if that's the case. Relatively speaking, bones are very resistant to heat. After a couple hours at the high temperatures that you get in lava, all of the soft tissue would have been gone, including the soft tissue parts of the bones. So that's actually pretty important. So, like we were saying before, bones aren't just that calcium and phosphorus minerals. In fact, in a human body, I think it's something like 5 pounds are actually the dry weight of the bones. Most of the weight of the bone is actually in the blood and the marrow and these other things inside the bone, which are softer. And which wouldn't survive 1200 degrees Celsius. So you don't get that slow replacement of the soft tissue with mineralized tissue or minerals in general that you need for optimal fossilization. So that sort of flash boiling and like burning off of everything on its own makes it really susceptible for being destroyed in the long run and not fossilizing in metamorphic rock. The high heat also leaves the bones very brittle, so they're likely to crumble before being fossilized, possibly even before the lava hardens. So according to the USGS, deep lava flows can take decades to solidify. For example, 10 to 15 meter or 33 to 50 foot thick lava solidifies after about 8 months to 1.5 years.
Wow.
Yeah, because it's so hot. It's sort of, I kept thinking about a pizza or like a calzone or something analogy, where the outside might be pretty cool.
Right, but inside it's still hot.
Exactly, because it's got just so much heat in there and it gets trapped in as the outside cools a little bit, that it stays fairly molten and at least able to move around. And you can imagine if there's a bone in there that's really brittle and things are shifting around it, it could pretty easily destroy that bone inside the lava. It gets even longer just because it's fun. I want to go through the other time periods. If a lava flow is 20 to 30 meters or 65 to 100 feet thick, it takes about 2.5 to 6 years to solidify. And, quote, the 1959 Kilauea Iki eruption, the approximately 135 meter, 440 foot deep lava lake, took about 35 years to completely solidify.
Oh my gosh.
End quote. So you can imagine 35 years of this being well above 200 degrees Celsius is going to do some serious damage to even bone, which is inside it, because it's going to be shifting around. The bone's already pretty fragile from all the other soft tissue being burned away. And all that extra weight, especially if you're talking about tens or hundreds of feet or even meters of lava on top of it, is a lot of crushing force. You can see how bones aren't usually found in metamorphic rock. However, it's not impossible for bones, teeth, or other material to survive a lava flow, but it is very unlikely. A recent paper proposes a few other occurrences of fossils in igneous rock. The title of the paper is, quote, The Fossil Record of Igneous Rock.
Very direct.
This is by Iverson et al. In Earth Science Reviews in 2020. And they point to the fact that remains can leave a cast, which is later filled like a mold, creating a fossil. Or like you said earlier, the cast itself can be considered a fossil. So in the case where it doesn't shift too much, but there was a bone that survived, at least in the beginning, and then if the rock completely hardens in that position, even if the bone is completely destroyed, you could still see the remnant of that bone. Or if something comes by later and fills that mold, then you have that cast replica, basically, of the bone. It's also possible for ichnofossils to preserve, for example, burrows being filled by lava or ash, I suppose, and signs of archaea from billions of years ago have been found in igneous rock. There's also chemo fossils, like you talked about earlier, those chemicals created by extinct animals, which can be preserved, again, for billions of years in igneous rocks.
Yep.
So especially when you're looking into the longer term fossil record, igneous rocks can be pretty useful. Less so for things like dinosaurs, though. I just wanted to point it out because a lot of sources will say that you only ever find fossils in sedimentary rocks, and that's just not the case.
Yeah, didn't think about the igneous.
That's the craziest one. I was actually planning on explaining why you only find fossils in sedimentary rocks. The first thing I found said, the bones melt in lava, and I thought, that doesn't seem right. So I looked up the bone melting point. I went down this whole cremation rabbit hole, and no, bones don't usually melt ever, unless they get really deep down into the earth. So yeah, anyway, this is the result of the rabbit hole.
All right.
You can find fossils in igneous rocks.
Hopefully, to you, our listener, you've learned everything you wanted to know about fossils, at least gotten a good overview of it.
And how and where to find them.
That wraps up this episode of I Know Dino. Thank you for listening. Again, if you want to check out the sources for this episode and go down your own Arictodromaeus burrows, then there will be links in the show notes at iknowdino.com. Thanks again, and until next time.